So we started with a quiz. Let's quickly solve it. Okay. Now I have a hollow wire, which means it's empty on the inside. So there is an inner radius A and outer radius B. Let me first solve the second part. What is the current density J within the wire? Now, current density, how did I define it? J magnitude will be the total current divided by the area. But which area is that? It's the area where current actually flows. So it's the area, the cross-sectional area between inner radius A and outer radius B. So as it's uniformly distributed, current density is uniform. This should be I over pi B square minus A square. Good. Now, what is the resistance of a section of wire that has length L? So I have this hollow wire. I cut a section of length L. What will be the resistance? If there is uniform electric field inside, how much? What will be the current density on the inside? That was the definition of my resistivity. It will be 1 over rho times the electric field magnitude. If I have electric field E, what is the potential difference between the two ends? It will be E times L. If J is E over rho, what's the current? It will be A times E magnitude over rho. So this is going to be pi B square minus A square times E magnitude over rho. The resistance is going to be delta V divided by the current, E times L divided by pi over B square minus A square times E magnitude divided by rho. So it's going to be rho L over pi B square minus A square. How many of you found this answer? Great. That was an easy quiz. Everyone did it. I'm very happy. You did not do it? No. So, okay, that's, okay. I mean, I keep answering this question, but I think that's important. Most of you come here through this university examination, university entrance exam system, which values answers and answers only. It doesn't really care how you arrive at the correct answer. It doesn't even care if you know the theory. It's an exam designed on choosing the most reasonable looking answer among 5 choices, which is terrible training for real life. Okay. Let's I mean, not even think about physics 102 quizzes. Let's say that you've actually become, somehow managed to graduate and became an engineer. You go to a client and he asks you, what's the value of the resistors I should put in my circuit? And you say 5 ohms. He puts in 5 ohms and all the thing blows up. That's not good. You have to be able to explain yourself. You'll say, hey, if I put in a small resistance, it will have a lot of current. If I put in large resistance, that will be too small to give any power. So by my calculation, I find it to be 5 ohm. And when you show it to him, maybe he'll say, hey, there is a factor of 10 missing here. It should be 50 ohms. All right? That's how science, business, everything proceeds. You should be able to express yourself on paper. That's very important. Not only for physics 102, but for all your courses, okay? So you wrote the answer right away here. If it's wrong, you'll get 0. That's all I can say. Any other questions? Good. Now, let's see. Let me remind you what happens if I start building larger circuits. For example, if I take two resistors, R1 and R2, what is the equivalent resistance of this circuit? Well, if I tie up this circuit to a battery with V volts, it's going to create a current I. Now, what is the voltage drop across the first resistor? The voltage drop, delta V1, is I times R1, right? Voltage drop across the second resistor is delta V2 is I times R2. So what's the total voltage drop from one end of the circuit to the other end of the circuit? V must be delta V1 plus delta V2. So it's going to be R times R1 times I1 times R2 times I, or V is R1 plus R2 times I, which means my equivalent resistance for series resistors is just the sum. All right? Series connection. How about if I connect those resistors not in series but in parallel? So R1 here, R2 here, and if I connect them to V volts. Now, here, obviously, the voltage drop across the first resistor is equivalent to the voltage drop across the battery itself, right? So delta V1 is going to be V, but what's delta V1? If a current I1 is passing through there, I1 times R1 is V, delta V2 if a current I2 is passing through, it's V. I need one more equation. I don't know what I1 and I2 are, and I don't have enough equations to solve. What do I need? I need the total current, right? If I'm going to find an equivalent circuit, I must look at the total current that's going into that circuit. So what's I? Now, obviously, if I current is coming in, it's split into two arms, I1 and I2. I expect I1 and I2 to add up to give me I. So it's going to give me, now I know what I1 is. I1 is V over R1, and I2 is V over R2. Now, the total current I is V over R1 plus V over R2. So 1 over R1 plus 1 over R2 times V. Or I can say V is 1 over R1 plus 1 over R2 times I, which means my equivalent resistance is 1 over R1 plus 1 over R2, or I'll remember it as R equivalent inverse is R1 inverse plus R2 inverse. All right? I'm not going to talk more about these because I think most of you know these from high school, these relations, right? Now, What happens if I have a more complicated circuit? Let's say that I'm trying to draw a circuit. One ohm, 2 ohms, 2 ohms, 1 ohm, and 1 ohm. And if I want to find the current here, given that voltage here is 5 volts. How do I do this? Any suggestions? Sorry? You're right. But how would that help me? There are clearly, this circuit cannot be reduced into parallel and series resistors. Right? So maybe I need something deeper. And we have already intuitively stated the principles we have. All circuits can be solved by the two following principles. First, when I was looking at series resistors, I immediately said voltage drops are additive. So if I actually went through a loop here, what are the voltage drops through the loop? Here is minus plus, so my first voltage drop was minus V across the battery. Then I have delta V1, but I'm entering it from the plus terminal, so I'll have delta V1, then I'll have delta V2. Then I came back to the same point. What happens, what's the voltage difference between a point and the same point? If I go through any loop, there is no voltage difference, right? I came back to the same point. That was our first principle, right? So my first principle, we intuitively know this, potential depends only on initial and final points. So delta V, the change in potential on any loop, is 0. I'll state a second principle, and you already intuitively know what that principle is. I'm sorry. When I was looking at parallel resistors, at the point here, I said there is a node here. If current is coming, it must split into two arms. So I said, if I look at the current coming into this node, I is coming in, minus I1 is coming in, which means I1 is going out, minus I2 is coming in, which means I2 is going out. They all add up to 0. Why did I say that? What happens if these currents, if the total incoming current to any point is not 0? What was current? Charge per unit time. So if I had a node, if I had an element where all the currents were coming in, added up to some value, charge must accumulate there. I would be constantly adding charge to that point. And I know charge is conserved. It doesn't accumulate at the conductor. Okay. Whatever is coming in must leave. That's the requirement for equilibrium. So I can state at any node. What's a node? Node is where more than one conductor, more than one wire meets. Okay, so it may be a triple node, it may be a quadruple node. There may be many wires crossing. Incoming I sum must be 0. Now these are very intuitive, very simple to remember rules. If we just said that, that would look bad. We need a sexy name for them. We want to impress our grandmother. We are going to call these Kirchoff's laws. The first one is called Kirchoff's loop law or Kirchoff's voltage law. The other one, the second one, is called Kirchoff's node law or Kirchoff's current law. But you see, these are not relying on some super mysterious physical principle. The first one is the definition of the potential. For any conserved field, for any conservative field, if I go around the loop, I come back to the same potential. And the second one just depends on conservation of charge. If I have a piece of wire, I don't care how many legs are coming in, the total incoming current must be 0. Whatever is coming in must go out, otherwise charge would accumulate inside. And we don't want that. Okay? Now let's actually go back to our circuit and try to solve what that current is. Alright? So what I'll do is what happened? I didn't want that. I wanted to be able to carry it. Maybe I should. I'm tempted to try again. Let's solve the circuit by Kirchoff's laws. Okay. Well, some of the stuff is left behind. 2 ohms and 1 ohm is left behind. So 2 ohms and 1 ohm. How am I going to solve this circuit? First of all potentials, all potentials we need are relative values, right? So I need a reference point. I can always choose one point in my circuit to be at 0 potential, okay? That's what I'll do. I'll choose one point here, and it's generally shown by this sign. It's called the ground sign. I'll say this conductor is at 0 volts. Well, basically all of the conductor here is at 0 volts, all right? Now, I have a battery here. So can you tell me what's the potential of the conductor here? Well, it's across the battery, so it must be exactly 5 volts, right? What other nodes do I have in this problem? Sorry. I have node, let me call this V1. And another node V2. I don't know the potential values for these 2 nodes. So if I know the potentials for these nodes, I can find all the currents. Let's try to find out. Let's find out. Let's write it with blue. Now, let's look at the node here. I'm going to look at all the currents going out from that node. I'll call this I1, I'll call this I2, and this one I3. What is I1? The node here is at V1. The other end is at 5 volts. So I1 is V1 minus 5 volts divided by 2 ohms, right? Delta V over R gives me the current. Should I do it once again? One end of the conductor is at V1, the other end is at 5 volts. So the potential difference across the conductor is V1 minus 5. The resistance value of the conductor is 2, so the current must be V1 minus 5 over 2. How about I2? One end is at V1, the other end is at V2. No, it's not at 0, it's V2. Divided by 1, that's the resistance. How about I3? Now, one end is at V1, the other end is at 0, and it's over 1. So now, what's the total amount of current leaving that node? I1 plus I2 plus I3, right? So I1 plus I2 plus I3 must be 0. This is Kirchoff's current law. The total current leaving a node must be 0. Whatever is coming in must go out. Good. So I'm just writing the values here. V1 minus 5 over 2 plus V1 minus V2 over 1 plus V1 over 1 is 0. Let me multiply by 2. V1 minus 5 plus 2V1 minus 2V2 plus 2V1 is 0. 5V1 minus 2V2 is 5. This is going to be my first equation. Let's look at the next node, V2 node. And I should do it in another color. I'll call this I4, this guy I5, and this guy I6. Can you tell me what I4 is? One end is at V2, the other end is at 5 volts divided by 1 ohm. How about I5? Well, I5 is just minus I2, right? It's in the other direction, right? So I can maybe just right away say one end is at V2, the other end is at V1 divided by 1 ohm. 1. How about I6? I6 is going to be V2 minus 0 divided by 2. And again, Kirchoff tells me that if I sum the currents going out of this node, it will give me just 0. So let's write all the things. V2 minus 5 plus V2 minus V1 plus V2 divided by 2 is 0. I'm going to multiply by 2, 2V2 minus 10 plus 2V2 minus 2V1 plus V2 is 0, or 5V2 minus 2V1 is equal to 10. That's my second equation. I have two unknowns, I have two equations. Can I solve them? Yes, let's solve them. Let me rewrite those equations. 5V1 minus 2V2 is 5, and 5V2 minus 2V1 is 10. How do I solve such a set? Let me try to get rid of one of my variables. So what I will do is, I'll multiply the first equation by 2 and the second equation by 5. Okay? So I'll find 10 V1 minus 4 V2 is 10. And in the second equation I have 25 V2 minus 10 V1 is 50. If I now add these side by side, what do I find? 21 V2 is 60. V2 is 60 over 21 volts. How about V1? From the first equation, V1 is 5 plus 2V2 divided by 5. So it's going to be 5 plus 120 over 21 divided by 5. Or it's going to be 1 plus 20, what? I can't divide 24 over 21, right? So it's going to be 45 over 21 volts. Okay? Did I finish my question? Not quite. This is V1. What do I need? I need to find the total current. The question asked originally the total current here. So what would that total current be? The total current will be, I would be 5 minus V1 over 1 ohm plus 5 minus V2. I'm sorry, this is 2 ohm and this is 1 ohm. So I need 5 minus the total current is 5 minus V1 over 2 plus 5 minus V2 over 1. Just putting everything together, 5 over 2 minus 45 over 21 plus 5 minus 60 over 21. Now I think there is another 2 here. So 15 over 2 minus 45 plus 120 over 42. It's going to be 15 times 21 minus 165 divided by 42. I am extremely lazy. So I didn't want to call up my calculator. Instead, I'll just write 16 times, what was it? 21. 15. Why? I don't know why I said 16. 15 times 21 minus 165 divided by 42. 3.57 amps. Does it make sense? Oh, okay. Not too bad. I think it's okay. Now, I think you all may be a little bit confused here. I may have moved super fast. This looked like a lot of calculation for such a simple circuit. I did this on purpose. I just wanted to show you that Kirchoff's laws are very simple to write down and very simple to apply. Actually, they are so simple to apply that you can write computer programs which can find out the currents and voltages in a circuit. Probably most of you who are in computer science and electrical engineering, they are going to have a circuit analysis course where they will actually use such commercial programs. You'll just print out, you just define the circuit to your computer and it can immediately tell you where the currents are, what their values are, what the voltages are. But you see, we can also do it because all of this depends on a very, very basic principle. Charge conservation and conservative fields. The potential difference is zero. Okay? So I think what you actually have to learn from today's lecture is that Kirchoff's laws are not something magical, and it's easy to apply them if you have used them enough times. You need some practice to be able to build up insight, not because when you become an engineer you will actually have to calculate currents for huge circuits. You have to understand what's going on to have some insight about how to design a circuit. That's why it's important to learn and apply Kirchoff's laws a few times. All right? Any questions? No? Okay. Now let me talk about one more thing in preparation for our lecture on Wednesday. What happens if I put in capacitors to my circuit? So what's the capacitor as a circuit element? How does it behave? For example, if I actually take a capacitor and initially charge it to plus Q, and then connect it to a resistor with a switch and close the switch, what do I expect to happen? Now, there are plus charges here and minus charges here. When the switch is open, plus charges cannot migrate to the minus charges because they don't have any path. They actually have to jump over vacuum to get there. They can't do that. But as soon as I actually close the switch, what will happen? Plus charges will start migrating through the resistor to the minus charges. So what will happen eventually at the very end of the day, if I wait long enough? All these plus charges must have gone to the other terminal and they must have neutralized the minus charges. So at the end of the day, I expect the capacitor to be fully discharged. But initially, when I charge a capacitor, I also store some energy. What happens to that energy? When charges are moving through the resistance, what do they create? They create heat. So this initial stored energy will be turned on into heat in that resistor. Okay. So our aim, very quickly, is to find how this initial energy is turned into heat. What I would like to find out is what's the current here as a function of time. Right? And I'll do it. It's not too hard. So here is my circuit. When the switch is closed, I have a current here, I of t. And now the charge on the capacitor will also depend on time. I expect it to go down with time. Now, if the charge on the capacitor is Q, what is the voltage on the capacitor? Voltage on the capacitor must be Q over C, right? That's the rule for capacitors. Voltage is the charge divided by capacitance. But I can also write another formula for this V of t. This V of t is the same potential is seen by the resistor. So what's the current? It must be V of t divided by R. Here's a resistor. I have a resistor here. Right? So in other words, I can say I of t is Q of t divided by RC, if I combine this. But now, what is the source of this current? Where are these charges coming from? They are coming from the plus terminal of my capacitor. Right? That's their origin. So if I run current out of this plus terminal, this current is coming out of the plus terminal. All the current is leaving my plus terminal. So remember the definition of my current. It must be the time derivative of the charge stored in the capacitor. But be very careful now. Is the current coming into the plus terminal or is it leaving the plus terminal? It's leaving. So the charges are actually, so if there is positive current, Q, capital Q must be going down. So there is a minus sign in front. Hey, I have two equations. Let me combine them. I see that minus dq of t dt is Q of t divided by RC. Or let me write it in a slightly better form. dq dt is minus 1 over RC Q of t. Now, this is the perfect place to scare you guys. I can scare you so much that today you will go ahead and actually go home and solve some examples just 3 days after the exam. I can say, this is a differential equation of the first order. We need the homogeneous solution also by the particular solution, so I can say big words. It is really a differential equation. Quite possibly it's the first time you actually see a differential equation. What does that mean? All the equations we have actually seen related the unknowns to other unknowns or to themselves. You solve the equations like 5x minus 3x is 3, right? But what's this now? It actually relates a variable, an unknown q, to its time derivative. So that's why it's called a differential equation. And there will be separate courses for you to learn to solve differential equations. So what are we doing now? Let me forget about this definition, differential equation. Let's look at the equation. It tells me there's a function of time, Q of t. I take a derivative and I get back the same function with a constant in front. Which function behaves like that? When I take the derivative of the function, I get back the same thing. Exponential, right? E to the x if I take, or e to the t, if I take a derivative, remains e to the t. So we'll actually solve this differential equation by inspection. I'll say if Q of t is a constant, I can always multiply it by a constant, is e to alpha times t. dq dt is going to be, if I take a derivative, alpha comes in front, alpha t. So now I can actually replace this to the left and right. Alpha times e to minus alpha t is minus 1 over RC, a e to alpha t. A is cancelled, e to alpha t is cancelled. So this alpha must be 1 over RC. How do I find the constant A? What's the charge at time t equals to 0? When I turned off the switch, it was Q. I defined it to be Q, right? Which is A times E2 minus 1 over RC times 0. What's e to the power 0? 1. So apparently A is Q. So what's Q of t? Q of t is Q, my initial charge, E2 minus T over RC. If I plot this as a function of time, what do I see? I start with Q, so this is Q of t. But as time passes, how does the exponential function behave? If it's a minus exponential, it actually decreases with time, right? That's an exponential decrease. It never quite becomes 0, you may say, but it actually decreases quite fast. Okay? An exponential decrease is so fast that it's almost, let's see, if time is equal to 5 times RC, then Q of t equals 5 RC will be Q times E2 minus 5. What's the value of E? E is 2 point something like this, right? So it's almost 3. 3 to the power 5 is 9 times 9 times 3. So 81 times 3, it's almost 200. So after 5 RCs, the initial charge drops to 200 of its value. So RC, R times C, is called time constant of the circuit. And it's actually quite interesting. What is the unit of this? This is called tau, is RC. Tau unit is, R unit is ohm, C unit is, capacitance unit is, come on, what was the unit for capacitance? Farad. But it's amazing, work this out yourself, we're going to do it the first thing next lecture. Ohm times farad is second. I find this quite fascinating that ohm times farad gives me second. So when you have a capacitor and a resistor, it actually tells me how fast it will take for this capacitor to discharge. Okay? And next time we'll look at this relation and we're going to look at the energy balance in this circuit. See you. Yeah. Of course, yes.